Section. Introduction. We're going to delve into the intriguing question of what information is stored within the hidden layers of large language models, LLMs. This is a crucial aspect of understanding and controlling modern AI, and it's been a hot topic of late. Various methods have been developed to interpret this information, but they all have their limitations. For instance, some methods use linear classifiers, known as probes, to interpret the hidden layers. However, this approach requires supervised training for predefined classes, which can be challenging when there are many classes or when not all categories are known beforehand. Another approach is to project the hidden representations into the model's vocabulary space. However, this method's accuracy decreases in the early layers, and the results can be difficult to interpret. Lastly, some methods intervene in the computation to identify if a representation is critical for certain predictions. However, these methods are not very expressive. They provide class probabilities or most likely tokens, rather than a high-quality explanation in natural language. In our work, we propose a new approach. We believe that the advanced capabilities of LLMs in generating human-like text can be used to translate the information in their representations for humans. We introduce a modular framework, called Patchscopes, that can be configured to extract various information from LLM representations. The idea is to decode specific information from a representation by patching it into a separate inference pass that encourages the extraction of that information, independently of the original context. A configuration of our framework, a patchscope, can be seen as an inspection tool geared towards a particular objective. We show that many existing methods, including those that rely on vocabulary projections and interventions, can be cast as patchscopes. Moreover, new configurations of our framework introduce more effective tools in addressing the same questions, while mitigating several limitations of prior approaches. Additionally, Patchscopes enables addressing underexplored questions, such as fine-grained analysis of the input contextualization process and the extent to which a more expressive model can be used to inspect hidden representations of a smaller model. We conducted a series of experiments to evaluate the benefits and opportunities introduced by Patchscopes, focusing on autoregressive LLMs. We found that using a few-shot token identity prompt leads to substantial gains over vocabulary projection methods. We also found that, despite using no training data, Patchscopes significantly outperforms probing in 6 out of 12 common sense and factual reasoning tasks, and works comparably well to all but one of the remaining 6. Beyond output estimation and attribute decoding, Patchscopes can address questions that are hard to answer with existing methods. For example, we were able to verbalize the gradual entity resolution process. We showed that in processing Alexander the Great throughout the layers, the model reflects different entities starting from Great Britain to the Great Depression, to finally resolving Alexander the Great. We also showed how one can further improve Patchscope expressivity by using a stronger target model. Lastly, we showcased the utility of Patchscopes for practical applications. We showed how it can be used to fix latent multi-hop reasoning errors when the model is capable of conducting each reasoning step correctly, but fails to process their connection in context. In conclusion, we propose Patchscopes, a general modular framework for decoding information from LLM hidden representations. We show that prominent interpretability methods can be viewed as instances of Patchscopes, and new configurations result in more expressive, robust across layers, and training data-free alternatives that mitigate their shortcomings. In the related work section, we discuss activation patching, a causal intervention commonly used for studying if certain activations play a key role in a model's computation. Patching has been used largely for localizing specific information to specific layers and token positions, and for finding paths explaining how information propagates in the computation. Despite certain limitations, patching remains a key tool for mechanistic interpretability. We argue that using patching only for localization purposes is myopic, and propose to use it for translating LLM representations into natural language. Very recently, patching has been used to study new problem setups, all of which can be seen as different configurations of our proposed framework. Inspecting the hidden representations of neural networks has gradually become an active research area. Probing classifiers are perhaps the most common among such efforts. Since the emergence of the transformer architecture, other inspection methods specific to natural language domain were born that use projections into the vocabulary space. While various other latent inspection methods exist, the above are the most relevant to this work, and as we show, many of which can be cast as different Patchscope instantiations. Section Summary. The section introduces the problem of understanding the hidden representations of large language models, LLMs, and the limitations of existing interpretability methods. The authors propose a modular framework called Patchscopes that leverages the text generation capabilities of LLMs to translate the information in their representations into natural language. They demonstrate that Patchscopes can outperform existing methods in tasks such as next token prediction and attribute decoding, and can also address questions that are difficult to answer with other approaches. The authors conclude by highlighting the contributions of their work, including the introduction of a more expressive and robust inspection technique and practical applications such as correcting multi-hop reasoning errors. Section: Patchscopes. In this section, we'll be discussing a concept we call Patchscopes, which is a new approach that enhances previous methods used for understanding how language learning models, LLMs, work. We'll be focusing on LLMs that use auto-regressive transformers, but the principles we discuss can be applied to other types of LLMs as well. Patchscopes is a method that uses the advanced capabilities of LLMs to generate human-like text. This is done by translating the information that is encoded in the hidden representations of the LLMs. In simpler terms, we take a hidden representation from an LLM, and then we patch it into a different LLM. This allows us to decode specific information from the hidden representation. However, it's important to note that this method doesn't guarantee that all the information is stored in the patched representation. Instead, it reveals if specific information can be decoded from the patched representation. This is a subtle but important way to expose the information that is contextualized within the hidden representation. To explain this in more detail, let's consider an input sequence of n tokens, which we'll call S, and a model M with L layers. The hidden representation at layer L and position I when running M on S is denoted as h_I_L. To inspect this hidden representation, we consider a separate inference pass of a model M** with L* layers on a target sequence T of M tokens. We then choose a hidden representation at layer L** and position I** in the execution of M** on T. We also define a mapping function that operates on hidden representations of M. This function can be a simple identity function, a linear or affine function, or even more complex functions that incorporate other sources of data. The patching operation refers to replacing the representation during the inference of M** on T with the function applied to h_I_L. This allows us to intervene on the generation process and modify the computation after layer L*. A Patchscope intervention is defined by a quintuplet of a target prompt T, a target position I in this prompt, a mapping function, a target model M, and a target layer L of this model. It's possible that M and M are the same model, S and T are the same prompt, and the mapping function is the identity function. We'll show in the following sections how this formulation covers prior interpretability methods and further extends them with new capabilities. Patchscopes can encompass prior methods. For example, recent methods inspect LLM representations by projecting them to the output vocabulary space. This is done by obtaining an estimation of the output distribution from the representation at position I and layer L. There are also methods that intervene on the LLM computation. For instance, some researchers have investigated whether it's possible to anticipate multiple generated tokens ahead from a given hidden representation, rather than estimating just the next token prediction. This method, called Future Lens, uses a target prompt that is different from the original prompt. More broadly, Patchscopes also covers recent mechanistic interpretability methods that analyze internal processes in LLMs with inference computation interventions. For example, causal tracing uses a source prompt augmented with Gaussian noise as the target prompt. In conclusion, Patchscopes is a versatile and powerful tool for understanding and interpreting the workings of LLMs. It builds upon and extends previous methods, offering new capabilities for interpretability. Section Summary. Patchscopes is a framework that extends prior interpretability methods for language models, LLMs, by leveraging the advanced capabilities of LLMs to generate human-like text for decoding specific information from their hidden representations. It involves patching a hidden representation obtained from an LLM inference pass into a different inference pass of the same or a different LLM, which allows us to examine if specific information can be decoded from the patched representation via the post-patching computation. This framework encompasses various interpretability methods, such as projecting representations to the output vocabulary space or intervening on the LLM computation, and can be applied to different LLM architectures. Section: Patchscopes enables novel inspection methods. The concept of Patchscopes opens up new possibilities for inspecting models. Previous research has mostly focused on using the same model and prompt for patching, but with Patchscopes, we can explore a variety of configurations that could potentially reveal new inspection capabilities. For example, by changing the target prompt, we can decode any feature we want, independent of the source prompt computation. We could use a prompt like, "the capital of X is," to see if the model can extract the capital city of a given country from its hidden representation at a specific layer. Similarly, a prompt such as, "tell me facts about X," can help us determine if the model has identified the entity name corresponding to a given description in a specific layer. Unlike probing, this method is not limited by the number of classes of the chosen feature. Also, if the model being inspected isn't expressive enough to answer certain queries, we can patch the representation into a more capable model. In the following section, we'll demonstrate how these new extensions significantly outperform existing methods for querying specific information in the computation of large language models, LLMs. We conducted several experiments to evaluate how well our framework can decode different types of information from LLM representations, including next token predictions and specific attributes. We also explored the new possibilities that Patchscopes introduce, such as analyzing the contextualization of entity names and using stronger models for inspection through cross-model patching. In one experiment, we wanted to estimate the output probability distribution for some input, which is obtained by multiplying the final layer last position hidden representation by the unembedding matrix. We were particularly interested in how early in the computation the model has made its final prediction from the given context. We tested this on multiple LLMs, including Llama 2, Vicuña, GPT-J, and Pythia. We compared vocabulary projection methods with a new Patchscope. Each method gives an estimated output probability by patching an intermediate representation to the model's final layer. We also looked at the common setting where the same model is used for both the source and target, and discussed extensions where different models are used. In one method, called logit_lens, we made no changes to the patched representation. In another method, called tuned_lens, we used an affine mapping function between representations at different layers. We fed the model examples from a training set, and for each example, we obtained a pair of hidden representations. We then used linear regression to find a matrix and a bias vector that minimized the difference between the two representations. In the token identity Patchscope method, we used a different target prompt from the source prompt to encourage the model to decode the token identity of the hidden representation. Unlike the previous methods, this method discards all the information from the source prompt computation, except for the patched representation. We created a prompt with demonstrations representing an identity-like function. This Patchscope does not require any training. Section Summary. The Patchscopes framework introduces new configurations for inspecting language models by modifying the target prompt, allowing for the decoding of specific features detached from the source prompt computation. This approach is not limited by the number of classes and can be used to assess the model's ability to extract information or resolve entity names. Additionally, Patchscopes outperform existing methods for querying specific information in language models. Section: Evaluation. We evaluated our predictions on the pile evaluation set using two measures. The first measure, precision at 1, looks at the percentage of instances where the token with the highest probability in our predicted distribution matches the token with the highest probability in the original output distribution. The second measure, surprisal, calculates the negative logarithm of the probability of the token with the highest probability in our predicted distribution, according to the original output distribution. Our results showed that, starting from the 10th layer, the Patchscope method consistently outperformed other methods, achieving up to a 98% gain in layers 18 to 22. This suggests that the model's decoding process can be effectively used to examine representations of different source prompts. It also shows that in most cases, early layer hidden representations carry prediction information regardless of their context. However, in the first 10 layers, all methods perform significantly lower, with the token identity prompt performing similarly to logit lens and worse than tuned lens in terms of precision. This lower performance is expected as the first layers are responsible for contextualizing the input. We also explored the extraction of specific attributes. Classification probes are often used to check if certain attributes are encoded in hidden representations. However, they require training and prior knowledge of attribute classes. We found that repurposing Patchscopes for attribute extraction overcomes these limitations. It doesn't require training and isn't limited by a predefined set of labels. It can also capture complex relations better than linear probes due to its ability to leverage the model's non-linearities. In our experimental setup, we considered factual and common sense knowledge represented as triplets of a subject, a relation, and an object. We investigated how well the object could be extracted from the last token representation of the subject in any given input context. We conducted experiments on 8 common sense and 25 factual knowledge tasks. We used GPT-J6b and filtered the data to keep only the examples where the object appears in the model's continuation of the prompt up to 20 tokens. We sampled 5 utterances from the Wikitext 103 dataset that included the subject and used them as our input. We kept tasks with at least 15 samples, resulting in 5 common sense and 7 factual tasks with a total of 1,453 data points. We developed a Patchscope for feature extraction and compared it with linear probing as a baseline. For the Patchscope, we created a general verbalization of the relation followed by a placeholder for the subject. To extract the object from the entity representation in our input, we replaced the representation of the placeholder at a certain layer with the representation of the subject from the same layer, and checked if the generated text included the object. For the logistic regression probe, we used the set of unique values of the object in the training set as a proxy for the range of possible objects for a given relation. We trained a logistic regression probe for each layer that predicts the object from the last token representation of the subject. We used threefold cross-validation for training and evaluation of this baseline. Section Summary. The evaluation of the estimated predictions is done using 2 metrics, precision at 1, which measures the accuracy of the highest probability token in the estimated distribution matching the original output distribution, and surprisal, which measures the minus log probability of the highest probability token in the predicted distribution. The results show that the token identity Patchscope consistently outperforms other baselines, demonstrating the usefulness of leveraging the model's decoding procedure for inspecting representations of different source prompts. Additionally, repurposing Patchscopes for attribute extraction overcomes limitations of training and predefined labels, making it more flexible in capturing complex relations compared to linear probes. Section. Evaluation. We evaluated our method, Patchscope, by measuring how accurately it extracts attributes on average. We considered Patchscope to be correct if the text it generated included a specific attribute within the first 20 tokens. For the comparison method, called the probe, we considered a prediction to be correct if the attribute with the highest probability was assigned. Our results, which were averaged over a range of attributes, showed that Patchscope performed significantly better than the probe in half of the tasks we tested, despite not using any training data and having no restrictions on its output. The probe only performed better in 1 task. For the remaining tasks, the difference in performance between Patchscope and the probe was not significant. We also looked at how the accuracy of both methods changed across different layers of the source data. We found that Patchscope consistently outperformed the probe in the early layers, which supports our hypothesis that previous methods struggle to surface information in these layers. Patchscope was able to extract attributes significantly earlier, even though this doesn't mean the attribute is explicitly encoded in a representation. In the middle layers, Patchscope performed similarly or better than the probe. However, we noticed that Patchscope's performance dropped in the later layers. We think this is because the representations in these layers are more focused on predicting the next token, so the attribute of interest might not be as easily accessible. We also looked at how language models resolve entity mentions across multiple layers. This is a complex process that involves contextualizing the input tokens of an entity and determining at which layer the entity is fully resolved. We used Patchscope to analyze how language models contextualize input entity names. For our analysis, we used a template to decode an entity description and applied it to the hidden representation at the last subject position in the source prompt across the early layers. This allowed us to see how the model describes the subject in each layer. We used the 200 most popular and 200 least popular subject entities from a dataset for our source prompt. We expected that the popular entities would be easier for the model to resolve, while the rare entities would be more challenging. We then evaluated the generated descriptions against descriptions from Wikipedia. In conclusion, our results show that Patchscope is a promising method for attribute extraction and entity resolution in language models. However, there is still room for improvement, particularly in the later layers. We believe that using a more expressive mapping could improve attribute extraction accuracy in these layers, which is something we plan to explore in future work. Section Summary. The evaluation of the Patchscope method shows that it achieves higher accuracy than the probe method in attribute extraction tasks, with significant differences in 6 out of 12 tasks. The performance breakdown across source layers reveals that Patchscope consistently outperforms the baseline in early layers, performs similarly or better in middle layers, but shows a decline in later layers, suggesting that the representations shift towards next token prediction. Analyzing entity resolution. Patchscopes are used to understand how LLMs contextualize input entity names across multiple layers, providing insights into how the model describes the subject in each layer. Section. Results. We'll now discuss the results of our study. We've created a table that shows the text generated by 2 different models for 2 subject entities. We've manipulated these models by altering their representations at various layers to match a target prompt. We've noticed that for most entities, the process of contextualizing is spread across the initial layers, with the last subject token pulling from more distant positions across these layers. We can see this trend by comparing the generated descriptions to those from Wikipedia, using a measure called Rouge L. In our figure, we've denoted the 2 models as M and M. For both models, the similarity increases in the first 5 layers and then slowly decreases. This decrease might be due to the representation of the placeholder token, X, remaining in the early layers when we apply changes to a later layer. This issue is only relevant for multi-token generation scenarios, as future positions can still attend to the placeholder position in early layers, potentially interfering with the model's ability to accurately generate descriptions for the altered token. Interestingly, the scores for rare, long-tail entities are significantly lower than the scores of popular entities, as we expected. We've also found that the smaller model seems to perform better than the larger model, possibly because the larger model is biased towards output generation at the expense of input contextualization. Overall, this analysis shows that our method, which we call Patchscopes, is useful for inspecting the contextualization process in early layers of language models. We've also explored the idea of improving inspection capabilities by explaining one model with a more expressive model. In the context of Patchscopes, this means altering a representation of model M into a more expressive model M**. We've found that when we alter models from the same family, such interventions are possible and can improve expressiveness. Specifically, we've looked at altering representations across different sizes of 2 models, Vicuña and Pythia, and measured how well the larger model estimates the next token predictions and entity resolution process of the smaller model. We've repeated our experiment using the token identity Patchscope. To overcome discrepancies between the models, we've learned affine mappings between their layers. Our results show that altering with a simple affine Patchscope is effective, with precision of up to 0.7 and 0.8 for Vicuña and Pythia, respectively. Specifically, altering representations to an early layer of the larger model seems to be the most effective. We've also found that using a large model as M** can enhance the output expressiveness. We've repeated our entity resolution experiment with the Vicuña model family, and found that altering from a smaller model to its larger version generally improves the ability to inspect the input contextualization, both for popular and rare entities. Finally, we've applied our findings to the problem of multi-hop reasoning. This is a challenging problem where a language model may be able to correctly answer each step independently, but still fail at processing the connection between different steps, resulting in an incorrect prediction. We've shown that Patchscopes can improve multi-hop reasoning performance without generating the reasoning steps, particularly in cases when the model fails at completing a multi-hop query despite being successful in each reasoning step independently. Through Patchscopes, we can surgically operate on the model representations, reroute the model's intermediate answer to one step of the reasoning task, simplify the consequent reasoning step, and ultimately correct the final prediction. Section Summary. The results of patching representations at different layers of two subject entities show that the contextualization process is spread over the first layers, with the last subject token encompassing more distant positions across layers. The similarity between the generated descriptions and the descriptions from Wikipedia, as measured by Rouge L, increases in the first 5 layers and then slowly decreases, potentially due to contamination caused by the placeholder token X remaining in the early layers. Patching representations across different sizes of models from the same family improves expressiveness and enhances the output expressivity, particularly in cases when the model fails at completing a multi-hop query despite being successful in each reasoning step independently. Section: Experimental Setup. Let's simplify the given text. In our experiment, we use a notation system where we represent a relationship between a subject and an object as a tuple. For instance, we denote the relationship between a subject entity and an object entity as a tuple, tau_1, which consists of sigma_1, the subject, rho_1, the relationship, and omega_1, the object. We also have another tuple, tau_2, where the subject is the same as the object in tau_1. We then create a multi-step reasoning query using these tuples. This query is made up of 2 parts. The first part, pi_1, is a verbalization of the subject and relationship from tau_1, from which we can infer the object. The second part, pi_2, is a verbalization of the relationship in tau_2, from which we can infer the second object after combining it with pi_1. For example, if tau_1 represents the relationship, Visual Basic is a product of Microsoft, and tau_2 represents Microsoft's CEO is Satya Nadella, we can verbalize these tuples into pi_1 as the company that created Visual Basic Script, and pi_2 as the current CEO of. This allows us to generate a multi-step reasoning query, the current CEO of the company that created Visual Basic Script. We then generate all valid multi-step reasoning queries where the object in tau_1 is the same as the subject in tau_2. We conduct our experiments on a dataset called Vicuña 13b, focusing on samples where our model accurately represents both tau_1 and tau_2 independently. This process gives us 1,104 multi-step reasoning samples, 46 of which meet our criteria and are used for evaluation. Next, we introduce a method called chain of thought, COT, Patchscope to improve multi-step reasoning. This method intervenes on the computation graph and reroutes representation to capture the object in tau_1 in place of the subject in tau_2. We compare this method with a baseline method, which is a simple generation of our model conditioned on the query without any intervention. We evaluate the outputs in terms of accuracy. Our results show that while the baseline accuracy is only about 20%, the Patchscope method achieves 50% accuracy. We find that patching representations from most source layers into early to mid layers is most effective in making the right prediction. Patching into late layers is not effective because the relationship in tau_2 has already been processed and the result has been copied to the last position. Therefore, it cannot incorporate the proxy of the subject in tau_2. We also observe that patching into layers that are less than or equal to the source layer is more successful on average.